Hello everyone, my name is Mark. This is my partner TrieuVy. This is our MIPS project, trademarked. TM is supposed to be for our initials. For the agenda, we have the introduction of our project, then we have the ISA known as the instruction set architecture, the enhancements, and then the system hardware schematic.
And then I'll be going over the introduction, which will go over the Harvard memory architecture, the machine register sets, the data types, as well as the addressing modes. First, so we have the Harvard memory architecture. It follows the 1K by 32, and it is byte addressable. Notice how you can access each individual byte at a time of the data, and it also has the interrupt capability of the interrupt request and interrupt acknowledge by sending the interrupt request to the CPU or the MCU, and then the CPU will process and send an interrupt acknowledge back to the I/O memory module.
Question while we're there. So you said that it's byte addressable?
Yes.
So do you have a way of just getting back a byte? Do you have the control built in so you could actually do a load byte instruction?
It's when we increment the address and we're able to access each individual byte.
So you actually implemented that, because most people don't. They just always get back 32 bits.
Oh, it's the 32-bit that we have.
But do you have the capability of actually addressing one byte and getting back one?
No.
Oh, okay.
It's the word addressable.
Okay.
And then it also follows the big endian format. So the biggest value in the sequence will get stored at the lowest storage address versus the little endian. And then we also have the microcontroller unit, which has all the control signals for all of the instructions. And it acts as an intermediary between the microprocessor unit and the program memory, any data memory, any I/O ports, and any supporting devices. What's unique about the Harvard memory architecture, it has separate data memory and instruction memory.
Alright, so for the machine register sets, we have 32-bit registers, which ranges from the RS, RT, PC, IR, DN, ALU out, and then we have the 5-bit status flags, which ranges from the interrupt, negative, carry, overflow, or 0. And as from the chart you can see here, these are all the registers within the register file. Specifically to note is the stack pointer at 29 and the return address at 31. So the stack pointer is used for instructions such as the push and pop, and for the return address, jump and link.
So are those 30, go back for a second, Mark. You say 32-bit wide registers, RS, RT, PC, etc. Those are programmable?
Some of them have a load, but some of them don't, though.
No, in other words, can the programmer access those registers?
Certain one, yes, we can, to hold the value.
Like which ones? In other words, machine register set, usually we're talking about the programmer's reference registers, which I know are on the left-hand side, but I wasn't certain about RT, ALU out, DN. Are those registers that the programmer can access, manipulate, use for shifts or multiplies? Or?
So as for the PC, we are not able to, IR we're not able to. The high and low we're able to grab data from the multiplication and the division. And then ALU out, yes, we are able to grab data as well as DN.
Yeah, I know you guys, but I'm talking about programmer. So I'm a programmer. Do I need to know about ALU out? Is there an instruction where I can manipulate it?
No.
Okay, so you usually would hide those, or at least break them out as, you know, internal registers only. Yeah, okay, keep on going.
Alright, so for the data types, we have 3. Unsigned Integer, which is used for most instructions. It's 32 bits and ranges from the negative to the positive end. For the signed long, it's used for multiply and divide instructions because it holds 64 bits, which also ranges from the negative and positive numbers. And for the last one, we have the unsigned integer, which is used for any unsigned operations, such as add unsigned. And for this one, it only ranges from 0 to the positive numbers.
So for an addressing mode is a specification for generating an address of an operand at runtime. So it follows these 3 modes: immediate, register, and register indirect. So for the immediate type, we have the operand directly placed into the instruction, and then in the RTL we can see that we are taking the content from register 29, adding the immediate value of A, B, C, D, and store it back into register 29. The next one, we're having the register direct of using the register to manipulate data and store it back into a register. And then next we have register indirect mode. It is, if register contains an address, which we need to calculate the effective address by adding the content of R1 plus the immediate value to graph the effective address. It will the operand will present it in the effective address and then load it back onto that register 7.
Alright, so for the ISA, we have fetch, decode, reset, types, and interrupt. For the reset, the purpose of this state is to put all the registers either at a starting point or give them zeros or low active value. So as you can see in the RTL, program counter is going to get 0. The stack pointer is going to get a 3FC because that was the starting point. And also the reset can happen at any time during the decode, fetch, or execution states. And to get stack pointer to get the 3FC, we've added a option in our DA select mux in front of the D address where it could select the stack pointer, which is at 29 decimal. And for the fetch, there are 3 main things that are happening, which is the deassertion of the interrupt acknowledge after the interrupt service routine is performed, to update the instruction register with memory specified by the program counter, and the last one is to update the program counter by incrementing it by 4. And under the lines of operation, for the interrupt, if the I/O memory is sending an interrupt request, then it's going to perform the interrupt, else it's going to go to decode. And then this is talking about when IR gets the memory content from the instruction memory specified by PC, and then this is just incrementing by 4 to update the program counter. For decode, the purpose of this is to initialize RS and RT registers and to calculate the effective address before any instruction is going to be performed. And in the MCU, it's going to send it to the correct execution state based on the IR bits, and those bits will determine whether it's going to be immediate, jump, register, or an enhanced type. And if there's an incorrect function select, then we have it set to default where it's going to go to the illegal op state. And as you've seen in the operation, if bits 31 to 26 is 0, it's going to go to an R type or a register type. If it's 1F, it's going to go to the enhanced type, else it's going to be decoded as either jump or immediate. And these are the 3 binary formats from the baseline of the ISA, which I'll go more in depth right now. So for the register type, the reason why it's called register type is because we're manipulating data within all the registers in the register file. And as I said before, 31 to 26 has to be 0, and with bits 5 to 0 determining which register instruction will be performed. And if it's a shift, bits 10 through 6 will show how many times the instruction is going to be shifted. And with the register type, RD, which is bits 15 to 11, will be the destination register. For the immediate type, we're using bits 15 to 0 as a 16-bit immediate, which is used to calculate the effective address or as a source operand for arithmetic instructions. Also, 31 to 26 in this format will determine which type of immediate instruction will be executed instead of 5 through 0. For the jump type, it's the same thing with 31 to 26. It will determine whether or not which jump instruction to perform, while the rest of it from 25 through 0 will help calculate the address that the instruction will jump to. And you can see here in this mux that when PC select equals 2, PC select equals 1, this will be the jump, where it takes the upper 4 bits of the current PC and then concatenate them with the IR 25 to 0 and 2 zeros at the end. And for the enhanced type, it acts as a register type where bits 31 to 26, instead of being 0, will be 1F. And since we don't have any shifts, we zero that out. And also since we're using RT as a destination register for the enhanced type instructions, we've also zeroed that out. But it's still the same with bits 5 through 0, determining which type of instruction in this format that the processor is going to execute.
So we also have the interrupt capability. As the picture depicted the relationship between the CPU and the I/O memory module, we can see that it represents the handshake protocol when the I/O memory module sends out a request to the CPU. then CPU process it and send it back an interrupt acknowledge to the IO memory modules, telling that here is the address that you need to go to in order to perform that interrupt service routine. And the purpose is when it gets interrupted, is the processor must retain the state of the machine by pushing the PC and the flags onto the stack. And here are all the enhancements that we have. I know point all the shifts, the input and output are not, but we'll be going over those, plus with the enhancement that we have. So for the barrel shifters enhancement that we have, it also uses the register type binary format. It has the shift amount, Y-low, the function select, and the output of Y-low plus the carry flag. And then as you can see in the, we have initialized R1, R2, and R3, as well as R4 with the content of R1. And then we're going to start shifting R1, 1 hexadecimal value to the left one. And then next instruction is shifting R2, 4 hexadecimal values to the right. And then shifting, the next one is shifting right arithmetic of register 3 decimal value. And how the arithmetic works is you will shift the sign bit. And the data will get written into the correct register.
Alright, so for the branch less than instruction, what we're doing here is that if RS is less than RT, it'll execute a branch. So for the first part of the instruction in the RTL, we have RS minus RT to compare both registers. And as of a result, in the next part of the RTL, if the negative flag is raised, it'll execute the branch, else it'll just fall down and update the program counter. And as I've stated before, for this mux right here, for the branch, if PC select equals 2, then it will execute the branch, which is the PC out concatenated with the sign extension and the 2 zeros at the end. For the verification, we have R1 to R3 initialized with 1, 2, 3 respectively. And of course, with the BLT, the branch less than instruction, we have R2 being compared with R3, and obviously 2 is less than 3, therefore it is going to skip 6 instructions, which is highlighted right here. And since R9, R1, R2, and R3 are never being written to, that's why they have all exits. And it'll go straight to the label, which is right here, where we initialize the value in R15, therefore that's why we have this hex value written there. And therefore the instruction is verified.
Little bit confused on the BLT.
Yes.
It should be, as far as the assembly language for MIPS, that would be read if R3 is less than R2. You've got it in reverse.
Yeah. Probably the typo that we have in reverse order.
Is it a typo on the machine code or typo on the
Typo on the
assembly language?
the comment that we have.
Okay. Yeah, that was what was confusing.
And then similarly for the branch greater than or equal to, in fetch and decode, we're still performing the same thing of updating the IR, the PC, initializes RS, RT, as well as calculating the effective address. And then in the branch greater than or equal to, we are performing a subtraction, a comparison by subtracting RS and RT. And in the result of ALU, we are looking for 2 flags in specific, is the native flags, which is used to verify the inequalities between RS and RT, as well as the 0 flag to verify if they are the same value. If it's the same value, then the flag 0 will go off. Similarly, with the verification, we have the instruction memory, initialize R1, R2, and R3, and which with the branch instruction, we are comparing if R3 is greater than or equal to R2. If it is, if the condition is satisfied, then we need to skip 3 instruction, which is Louis, Ori, and break. And then we're gonna follow through with we're gonna go through the label of writing R1 to R4, R2 to R5, and R3 to R6, as well as initializing, writing to R15 with the value and to indicate that we have passed that branch.
Again, you had a typo on that one for your next version.
Alright, so for the input instruction, we can kind of think of this as a load for the I/O memory, and the reason why is because you're taking content from the I/O memory and putting it into one of the registers in the register file. So in the first part of the instruction in the RTL, we have the sign extension being calculated for the effective address. In the second part, we're going to use the effective address as a pointer for in the I/O memory to put data into the DN register. Then for the last part, we're gonna have the content of DN being rented into the register in the register file that's specified by RT.
So where was DIN in that diagram? Back a page. I didn't see DIN anywhere.
DAN is where it holds all the register below the AOU.
But in your diagram, I don't see it.
Yeah, this is the multi-cycle one. It's in the single cycle.
So that's not your architecture?
No.
Oh,
It
what,
just to show that we have it written in AOU out and moved back to the memory to be stored back into RT.
okay, probably shouldn't use diagrams that are not your, yeah. Okay,
Alright. Okay, so for the output instruction, we can kind of think of this as a store for the I/O memory, where content from the I/O memory will be put into, oh, I'm sorry, I had that reversed, where content from a register in the register file will be put into the I/O memory. So similar to the input, the first part of the instruction for an output will calculate the effective address. After that, we're going to have the content specified by the RT for one of the registers to be put into that effective address pointing to the I/O memory.
So in the verification, we use the instruction memory module 14 to verify for this. So in the interrupt service routine, it's just to initialize R16 as the base register to go to, 17 with the content to be shifting and outputting, and then register 18 to be the loop counter to keep track. And then in this I/O loop right here, we are outputting the register, we are outputting data from I/O memory specified by base address specified by register 16 with the index of 0, and then followed by that is we are shifting every single time, as well as changing the base address as well as the decrement of the loop counter. So we can see that every time we initialize, we are outputting to the value into the I/O memory module, and then these input instructions will write it back onto the register files.
Alright, so for the clear instruction, what we're doing is just filling in zeros for a certain register in the register file. So how we do this is, in the first part, we're going to write zeros to LU out. And the way that we do this, if you guys remember in the MIPS 32, there is a zero function for that. So that's how that RTL was executed. And then as for the next one, we just have LU out getting written to the RT.
can I ask you, Mark?
Yes.
Why did you think that you needed to add a clear instruction?
Just in case if you want.
Since we could just subtract a register from itself and clear it. Like, why have a new instruction that you could basically already do just by doing a subtract or an XOR? Just wondering what your thought process was.
Just because it just makes it like when you're looking at the format of the code, like the binary format, it just makes it a lot more convenient. Instead of you taking two registers, you could just have one instead.
As far as you mean in assembly language,
Yeah,
it reads better or something like that?
Yeah.
Okay.
And then for the verification, we have R1 to R3 being initialized with 1, 2, 3. And we just added the push and pop just to make sure it'll go through those for the next slides. But for the clear instruction, so R1 was initialized with 1 in the register, and then after the clear, you can see in the log file that it ended up having zeros, therefore it was verified. For the move, so we're pretty much taking the content from RS and putting it into RT. And the way we did this is that we added a mux in front of the S of the ALU, where it can take the previous value of LU out. So essentially we're just looping the value back. And in the first part of the RTL for the move, you can see that RS will be put into LU out, and then the second part with that mux being implemented, we can do ALU out of that contains the RS content will be put into RT. And this is not to get confused with the swap, because essentially in the end, both registers will have the same value that would be in RS.
Did you do a swap?
No, we wish we did though. That would have been a...
Because again, you're paying for hardware to do an instruction that can already be done without the hardware. But if you did a swap, I could see where to put the hardware in there might be justifiable. Because you could do a move just by adding 0 to a register and putting it in another register. I think we did that, right? Studying the ISA. So, you know, the customers don't want to pay for stuff that probably is already built into the architecture. If you did a swap, that's a totally different thing, because that's a brand new instruction that can't be done. Okay, something to think about.
Alright, so for the verification of the move, we have R1 to R3 being initialized with hex values. And then we have 3 move instructions where R1's content would be copied onto R4, R2 being onto R5, and R3 being into R6. And you can see in the log files that indeed R4 is the same value as R1, and then 5 is the same as R2, and 6 being the same as R3. For the no op, which is no operation, we would use this instruction if we need a delay where for 1 clock we're not doing any operations. And the way that we do this is the mux that I previously said that's in front of the S of the ALU, where we just loop the value of ALU out, as you can see in the RTL for no op.
So for the push, well, we are using the pre-decrement method. Essentially, we are pushing a content of data in a register onto the stack memory, which is managed by the stack pointer. So fetch and decode, we still perform the same step. Now we're saving the current stack pointer onto our S, and then decrementing it to, because we're using a pre-decrement method, so we have to pre-decrement to save the memory space, and then store, and then in push 3, we are going to store the RS value into, sorry, I skipped. So in the ALU out, we're going to move that ALU data into the memory module. The data memory module pointed at in order for RT content to be stored into that memory module. And then we're also, the data is currently sitting in the ALU of the stack, the decremented stack. We're going to write it into the current stack pointer to save.
Alright, so for the pop, it is a post increment. That's how we use the method for it. So essentially, we're just putting the stack pointer in the RS, and then we're going to have the stack pointer being put into the ALU out. And then we're going to go into the data memory where it's pointed by that stack pointer to be put in the DN register. And since this is post increment after, as you can see in pop 4, when the data and content is being put into a register specified by RT, we're going to increment the stack pointer by 4. And the last part of the pop is to update the stack pointer.
And then in the push and pop verification, we have initialize R1, R2, and R3. And then for the push, we are pushing the data from the register onto the data memory module as specified. And then we're also popping it out so to have the data available at the data memory in order to put it back onto the register 7, 8, and 9. And then lastly, we are doing a move to guarantee that the push and pop have successfully been executed.
Alright, so for the system hardware schematic, we have the top level, which is also known as our test bench or our test picture, which encompasses the CPU, the I/O memory, and the data memory. We'll then zoom into the CPU, which contains the MCU or the MIPS control unit, the instruction unit, and the integer data path. Alright, so this is the block diagram for our test picture. As you can see, the control words for each memory, which is the chip select, the read, the write, the address to specify which content to take out from each memory, and then also the wires for data flowing from CPU to data memory or I/O to CPU and vice versa. And also with the I/O memory, we have the interrupt, acknowledge, and the interrupt request wires as well. In the CPU, we have the MIPS control unit, which is the state machine that has control signals going to both the instruction unit and the integer data path. The only thing is with the instruction unit, it's only giving out the program counter and the sign extension and IR out. And for IR out, it's being specified by the D address, S address, and T address for the bits, which is based on the binary formats of each instruction.
Can you go back to there just for a second? It's a little quick. Where's the data in port? I can see ALU out coming out. Where's data in? Like from memory. Do you have a path? You must have a path somewhere.
Yeah.
I'm just not seeing it.
Yeah, that was actually supposed to be the dy signal. That was supposed to be an input for the integer data path.
See, okay, so you
Yeah.
just didn't get in that.
We didn't put it in there,
Okay,
yeah.
thanks.
And then in the instruction unit, we have the program counter, the instruction memory, as well as the instruction register. We have added this hardware change to add in the options to update the PC by either jumping or branching to a new instruction. And this is how we specify the concatenation for branches and jumps.
Alright, so for the data path, I'm going to point out the changes that we made to the design. So the first one's going to be extending the deselect mux, where we added the stack pointer and the return address. And the next one will be the mux before S address, where we also added the stack pointer to be chosen for that. Next one is going to be this S select mux, where we pretty much, as I stated before, it's allowed the previous value of LU out to loop around. And then for this mux, we extended it to have the flags where we concatenate the flags with zeros to make a 32-bit value. And then, yeah, I believe that was the last one.
And then in the ALUL, we have the MIPS, specify all the instructions, the division, as well as the multiplication, and then the barrel shifter is the new enhancement that we've added, taking in the shift amount to specify, and then the shift type, specify the function select, and the TN, which is the Y-low value. And then the multiplexer is to multiply any appropriate data coming from the other 4 modules.
Any questions? Okay.